conditional probability mass function. Now with respect to that we will find it. The conditional mean of y given x equal to 2 each. So it is defined as expected values of y given, so xi is 2 here, so mu y given 2. So this is by definition summation of all the possible values of yj expected values of y given 2, yj given 2. So actually the probability mass function here we are representing y given x here. So for given case here only this variable we are representing. So this is yj can take value 1 and 2, so that's why this is 1 into probability that y given x 1 given 2 plus 2 into probability of y given x 1 given 2, sorry 2 given 2. So this value we have to put 1 into y given x. So if you put y is equal to 1, this is 5 by 11, 1 into 5 by 11 plus 2 into y by 2 y by x, actually 4 plus 2 6 by 11, 2 into 6 by 11. So this is nothing but 5 plus 12 by 11, so this is 17 by 11. Now to find the variance we will use the simplified formula. So this is the mean, conditional mean. The conditional variance we have to, if you want to find, by definition the conditional variance, the conditional variance of y given x is equal to 2 is by definition expected. So this is variance of y given 2, so we say sigma square y given 2. The definition is expected values of y minus mu y given 2 whole square, and your formula become all the sum of all possible values of yj minus mu y given 2. So this is the mu y given 2, this value we have found, whole square p of y given x, y given yj given 2. Now note that using this formula it is complicated because you have to subtract all the possible value minus 17 by 11, that value mu given y by 2, you have to take this square and then you have to get this value. So we have the simplified formula. This is expected values of, we have to find y square given 2 minus expected values of y given 2, already we have found, this is then whole square. So this is the simplified formula we will use. First we will find expected values of y square given 2. So let find the expected values of y square by given. Now expected values of y square given 2. So by definition this is summation all possible values yj, it can take value 1 and 2, p of y given x, yj given 2. So this is nothing but 1 square into p of y given x 1 given 2 plus 2 square into p of y given x 2 given 2. So this is 1 into y given x 1 given 2, it is here. If you put yj equal to 1, this is 4 plus 1 5 by 11, this is 5 by 11 into 1 into 5 by 11 plus 2 square is 4, 2 square, so y square ij square 2 square, this is 4 into whenever if you put 2 here, 4 plus 2 6 by 11, so this is into 6 by 11. So then what finally we are getting, this is 5 by 11 plus 4 24, so 5 plus 24 by 11, so this is 29 by 11. So this is expected values of y square given 2. Hence using the formula sigma square y given 2, this is nothing but variance of y given 2, it is nothing but expected values of y square given 2 minus expected values of y given 2 whole square. So all the values are known to us now. 29 by 11 minus 17 by 11 whole square. So just you compute it. So whatever this value it will come. If you compute this, you can use a calculator to find it value. So 29 by 11 minus 17 by 11 whole square. So what we are finding, so just use a calculator here. It will be approximately 0 point, so just it is fraction 248. So you can check whether it is correct. 248 approximately it is 0.248. So this is, so just we have to know the method. So finally this computation you can do by calculator, but if without knowing this method how to find the conditional mean and conditional variance, you cannot able to come up to these steps. So after that it is just a simplification only. But I hope you have understood it. So for finding the conditional mean and conditional variance, you need to find first conditional probability mass function. With respect to that, you can only find conditional mean and conditional variance. So here this question we completed. Compute the conditional mean and conditional variance of y given xi is equal to 2. So that value we have find that conditional mean we have found. I think this value it is here 17 by 11, and the conditional variance is coming like 29 by 11 minus 17 by 11 whole square. This is approximately 0.248. So we completed this discrete part to find conditional mean and conditional variance. Now we'll discuss whenever similarly whenever continuous random variable cases, when if we consider the continuous bivariate random variable, how to find the conditional mean and conditional variances. If x and y are continuous random variable, let xy be a bivariate, let xy be a bivariate continuous random variable with the joint probability mass function. Sorry, it is a continuous bivariate random variable, bivariate continuous random variable or continuous bivariate random variable with the joint probability density function is fxy xy. The marginal probability mass function of x is fxx, and the marginal probability density function, we have just discussed probability mass function, that's why I am just it is automatically I am saying mass function, but it is a continuous random variable, so it will be always probability density function. It is joint probability density function is fxy xy. The marginal probability density function, because both are continuous random variable, so it has to be density function. The marginal probability density function of x is fxx, and the marginal probability density function of y is fyy. The conditional probability density function of y given x is equal to x is defined as, so you can remember that already we have discussed the conditional probability density function of y given x equal to xi. X is defined as, so this is f of y given x, y given x, here particular values of x, so this is fxy of joint probability density function by the marginal probability density function, provided fxx not equal to 0. So all those x only we can compute while fx is not equal to 0. Now we will define the conditional mean and conditional variance. The conditional mean of y given x equal to x is defined as, so here the notation is, so defined by, so this is it is also say expected values of y given x equal to x, so this is the notation, or mu y given x this is because it is continuous, so we'll take the integration instead of summation. So summation we will consider in discrete random variable. This will be y, this conditional probability density function, y given x dy. So this is the definition of conditional mean. And also the conditional variance, the conditional variance of y given x equal to x is defined by, so here we will take this notation. This is variance of y given x, with this notation also we use. By definition, this is expected value of y minus conditional mean whole square. So this is minus mean to plus infinity y conditional mean, conditional probability density function y given x dy. Sorry, so y minus the mean, conditional mean, this whole square if y given x, y given x dy. So now this is a little complicated to compute. We use the simplified form. So this is nothing but expected values of y square given x minus expected values of y given x whole square. This expected values of y given x already we defined here. Expected value of y given x is nothing but mu y given x. And what is expected value of y square given x? Where expected values of y square given x is nothing but minus mean to plus infinity y square f of y given x conditional probability density function y given x dy. So using this formula, so how they are equivalent we have already discussed for general cases, general random variables, so you can go through that. So this is nothing but the mean and variance with respect to the conditional probability density function when we are discussing the continuous random variables. So this is given here in this slide. You can see that xy is continuous bivariate random variable with joint probability density function f of xy. The conditional mean of y given x equal to x is defined by mu of y given x, expected value of y given x minus mean to plus infinity y f of y given x dy that we discussed, and the conditional variance is defined by this, and this also represented expected values of y square given x minus expected value of y given x whole square. Now if you ask then suppose you want to find conditional mean and variance of x given y, here it is y given x. So similarly we can define it. The just we are writing again, just similarly you have to just interchange x and y variable here, position of x and y. The conditional mean of x given y is equal to some value y is defined as, so this will be expected values of x given y, this is denoted as x given y, which is summation. This is because it is continuous, so just now we'll discrete, that's why again I am just writing it, but because of continuous cases we cannot do sum, we have to use the integration. Just summation will be summation will be replaced by integration. This is x multiplied by the conditional probability density function x given y dx. So this conditional probability density function also, here I have written conditional probability density function y given x. Similarly where we can write the conditional probability density function where conditional probability density function x given y, it is nothing but joint probability density function by the marginals of y, particular values of y, where this should be not equal to 0, otherwise you cannot, it will be undefined. Then the conditional variance, how we will find the conditional variance of x given y is equal to y is defined as, so conditional variance is like this: variance of x given y, so notation sigma square x given y, this is defined as x minus mu of x given y whole square, and it can be computed with this. This is x minus mu x given y whole square f of conditional probability density function x given y dx. So this is just earlier we computed here. So y given x, it is x given y. Now because it is little difficult to compute, we will use some simplified formula. It is nothing but expected values of x square given y minus expected values of x given y whole square. So expected value of x given y, already it is defined, x given y here. This is mu x given y. This is the conditional mean, and this is the second order conditional mean, where expected values of x square given y is nothing but minus infinity to plus infinity x square conditional density function x given y, this is small x given y dx. So for computation purpose we will use this formula and we will find it, so that whenever it will be convenient. Sometimes we can feel that this formula is convenient for some region, for some of the density function, then we can use that. But we see that this is from most of the example, just I observe, this formula is a little convenient to find the conditional variance. So let us do one numerical example here. Let us one numerical example. So for density function, here let us consider this numerical example for conditional mean and conditional variance, how to find that. So this example we have already done some of, so this is a revision for you, you can go through it again. So here because we need to find conditional probability density function and to find the conditional mean and conditional variance, so that's why we need this marginal function also. That's why we have to compute again. Long back we computed these things, so let us do it again. The joint probability density function of a bivariate random variable xy is given by this function. So let us write down this. The joint probability density function, the joint probability density function of a bivariate, continuous bivariate random variable of the continuous bivariate random variable is given by f of xy x comma y. This is equal to, it is a uniform distribution, constant whenever 0 less than y, get less than equal to x, less than 1, and 0 otherwise. So basically if you draw a curve, so this is 0, this is 1 0, this is suppose 0 1, then you take, so this is 1 1, this is the line y is equal to x, this line y is equal to x, so y less than equal to x means this region. So this is the region y less than equal to x, and also so yeah, so region covered by this. So now this is 1 in this region, so what will be the value of k? Determine the value of k, find the marginal probability mass function of probability density function of x and y. All those things we did it. Let's say if you can remember, then we can write it directly, otherwise you have to do it. So suppose, let us quickly find out. So suppose what will be the values of k if you take the integration minus infinity to plus infinity fxy dx dy, this should be equal to 1. So now if you do this integration, it will be non-zero in this region. So in this region actually y is goes to 0 to 1 and x for any position. So basically you can so basically if you first do the integration, assuming that this integration exists because it is a density function, we can change the order of the integration. So it will be easy because 0 to x, this is constant k. First we will do integration dy and then dx, and x is 0 to 1. For whenever x is 0 to 1, for any values of x, this limit is 0 to x. For y, this is 0 and upper limit is x. So which implies this is 1. So this become k y, then limit is x, then integration 0 to 1 dx, this is 1, which implies k into x square by 2, 0 to 1, this become 1, this is equal to 1, which implies k by 2 is equal to 1, which implies k is equal to 2. So I just quickly done it. So did it because you have already I have already done it before, so you can go through that also. This is just to do this integration, very simple. So then k become 2 because this area under this curve is half, only 1 by half of this. So this is a triangle 1 by 2 into 1 into 1, 2 half. So it is a uniform distribution. So that's why to become 1 you have to multiply this constant 2 into 1 by 2, this become 1. So that's why this is k become 2. So let us quickly find out the marginal probability mass function of x. The marginal probability mass function of x, sorry, marginal probability density function, because it is a continuous random variable. The marginal probability density function of x is given by, so f of x, this is minus me to plus infinity, f joint density function f of xy dx, sorry, it is integration with respect to y, but it is non-zero when x between 0 and 1, then only it is non-zero, and also if x between 0 to 1, otherwise this joint density becomes 0, so this will be 0. And also this is non-zero when the limit for particular values of x between 0 to 1, the limit of y is 0 to x, because this function is non-zero when, so this become k is equal to 2. So this is y limit is 0 to x, upper limit of y is x only. So this is 0 to x, this is 2 dy, so this is become 2x, and otherwise it is 0. Hence we will write out the marginal probability mass function is fxx, which is equal to 2x if 0 between x and 1, this is become 0, otherwise. So otherwise now we want to find the marginal probability density function of y also. The marginal probability density function of y is given by, so fyy, this is nothing but minus me to plus infinity fxy xy, in this case we integrate with respect to x. Now it will be non-zero, this joint density only if 0 y between 0 to 1, and then this value will be fyy will be for any particular values of y, this value will be, sorry, this value will be since this is non-zero, what will be the limit of x, because with respect to x, so lower limit will be y. So any particular values fix y here, the lower limit will be x and then x to 1. So that's why this will be nothing but x to 1 2 dx. So this is nothing but 2 into 1 minus x. So then the marginal probability density function of y is 2 1 minus of y 2 sorry, this is 1, so I made so many mistake, because we are doing the limit of x. So this limit is y to 1. So here it is mistake, this is y to 1, so that's why this will be y. So 2 into 1 minus y, so 2 into 1 minus y, so here it is correct, 2 into 1 minus y. Usually I am thinking y but writing x. So 1 minus y, whenever y between 0 and 1, this will be 0 otherwise, so this will be 0 otherwise. So we already computed those things, and then the next question, how to find probability 0 less than x less than half, 0 less than y less than half.